All right, so last week in chapter 7, we started looking at radicals and changing them to fractional exponents. And why do we need to know how to do that? Well, here's what I like to call last week work in this year's ACT. So here's an example. And we've got 27 over 64 raised to the negative 2/3. Well, initially, if you look at that and you're not familiar with fractional exponents, you skip this problem, right? And so let's look through the parts of it. So initially, we don't like that negative 2/3. So the very first thing that we're going to do is flip our fraction over, because we know when we change sides, we change the sign. So we changed the sides that they were on. And now we have to a positive 2/3, 64 on top. Now, what does that really look like in a radical? Well, it really looks like the cube root of 64 squared over 27 squared. And if we were to solve that out, we could say that 64 is 4 times 4 times 4. But I've got it squared, so I've got two groups of those. And then 27 squared is 3 times 3 times 3, and I've got two groups of those. And so I need 3, I have 3, I'm going to have 4 times 4 over 3 times 3, and get 16 over 9 as my answer there, okay? We could also change this from this point and say, oh, 64 is 4 cubed, and 27 is 3 cubed. And so I've got 4 cubed raised to the 2/3 and use my power to a power rule. So 3 times 2/3 gives me just 2. So we end up with 4 squared. On the bottom, 3 cubed to the 2/3. Again, 3 times 2/3 just gives me 2. And so I've got 3 squared, and we've got 16 and 9 that way. And there's another example here at 23. It says for all positive real numbers A. And this looks super complicated when we first look at it, and right away some people just want to go ahead and skip that. But let's change it to fractional exponents instead of dealing with the radicals right there. So fractional exponents, right away we have A. I have 36, I need 3, so I'd write it as 36 over 3, which we can see right away cancels out and becomes a to the 12th. So now I just have a to the 12th raised to the 1/2. I've got a power to a power. 12 times 1/2 gives me 6. So that quickly simplifies down to a to the 6th that way. Okay, and then you practiced simplifying variables again, and simplifying some radicals with and without variables. And so sometimes we could go ahead and write it all out, find out that I need groups of 3, pull out our groups of 3 that way. One thing I do want to point out on these is that if there were something left over, so say this was really y to the 7th instead of y to the 6th, and so I'm left with a y left over. So I pull out 5y squared, and I'm left with a y underneath the radical. It is vitally important that the index that we start with be the index that we end with on that radical sign. Because if we don't write an index, we are assuming that it's 2. Okay? And we can't change indexes. And so again, make sure, like, if we start with the 4th root of something and we leave it underneath, we need to rewrite the 4 right there. So don't lose your index as you go, or else your problem will be wrong in that case, okay? Now, sometimes it is easier to rewrite a problem as a fractional exponent, because then you say, Miss Thomas, why did I have to learn how to do fractional exponents? Well, sometimes we can solve it easier as a radical. Sometimes we could just rewrite this 125 as 5 cubed, rewrite y to the 6th as y squared cubed, and then as soon as my index and my exponent match, those go away, and I simply just have my base. So I've got 5y squared, so I actually have my answer written right inside there, since I made my exponents match my index there. Okay, So same on this guy. Sorry, I had worked it out and deleted it. So we know that 9u squared v to the 10th all raised to the 1/2 is really the same over here as the square root of this. So we could work it all out and pull things outside the radical, or we could rewrite 9 as 3 squared, u squared, and v to the 10th as v to the 5th squared if we wanted to. And then all raise that to the 1/2. Well, this is a power to a power that gets distributed to each of these. So 2 times 1/2 is 1. So I just get left with a 3. 2 to 1/2 is 1. I get left with a u. Here's my 2 to the 1/2. I get left with b to the 5th. So a couple of ways that using our fractional exponents can make simplifying a little bit faster for that. Okay. So what we're going to move through this week is the first note page, 6.3 notes, where it says adding and subtracting radicals. And the important thing about adding and subtracting radicals is that just like when we had regular variables, everything has to match on it. And so if I had 3x plus 4x, we would combine that and say that's 7x. So in the same way, if I place a radical in that space of the x, everything about that radical must be exactly the same for addition and subtraction. Okay, and so the index has to be the same. In this case, we've got square roots. The base has to be the same. In this case, we've got 2. And so now I can add my coefficients there to be 7. And then my entire term of square root of 2 would stay that way. Now, if we had it as a fractional exponent, and I rewrote this as 3 times 2 to the 1/2 plus 4 times 2 to the 1/2, the rules still apply. The very first thing that we're going to look for is addition and subtraction, or multiplication and division. So we're looking at addition and subtraction. Everything about this has to be exactly the same. So our bases match and our exponents match. So we would simply add our coefficients. 3 plus 4 gives us 7, and then we still have 2 to the 1/2 as that term there. Okay. So what do we do when sometimes it doesn't look like our radicals or our exponents match? Okay. So sometimes it doesn't look like they match. Like in this case, I've got 3 times the cube root of 5x to the 5th minus 3 times the cube root of 40x squared. So in this case, when I'm looking at my bases, I've got like indices, but I do not have like bases on the inside. However, we can simplify those according to our radical rules. So let's do that first and then compare. So we can't make a decision yet about it. So I'm taking the cube root of 40x squared over here, and I'm going to write it out in its factored form. So I've got 8 times 5 times x squared, and 8 is 2 times 2 times 2. So I need 3. I have 3. I'm going to pull out this 2 and be left with 5x squared underneath. Okay, nothing else I can pull out. So then let's go look. I've got 5x to the 5th. Well, I only need 3 to pull out. And so I can pull out 3 of these x's, and they get pulled out as a single x. And it leaves me 2, because 5 minus 3 left 2. So now I have 3x times the cube root of 5x squared minus, here is my 2 initially and my x that I had. So 2x times the cube root of 5x squared. Now they are completely alike. Now my indices match and my bases match. So this is one single term that will stay the same, cube root of 5x squared. So I take my coefficients, and I have 3x minus 2x, which simply gives me a 1x, and I leave the cube root of 5x squared. Okay, so let's look at another one. The cube root of 16 minus the cube root of 2. Currently, they're not alike. But I could take 16 and make it 2 times 2 times 2 times 2. I need 3. I have 2. Sorry, I have 3. They'd come out as a 2 here up front. And I'm left with a single 2 on the inside. Now they do match. 2 cube roots of 2 minus a cube root of 2. This has an unwritten 1 as its coefficient. So I've got 2 minus 1 gives me 1. Which again, I don't have to write, but it would go right there if I was writing it. And then we leave our term as a cube root of 2 there. So when we were looking at our adding and subtracting worksheet that you've got there, if we were to look at this first one, number 1, we've got cube root of 27 and the cube root of 12. So right now, they do not match. We cannot do anything because it is subtraction. But could we make them match? Now, these do not have an index, which means we have an assumed index of 2. We are looking for the square root of that. So 27 is 3 times 3 times 3. 12 is 3 times 4, which is 2 times 2. So I need 2, I have 2, I'm going to pull him out. I leave the 3 that already existed. Now I have a new 3 on the outside, and I have the square root of the 3 left on the inside. My subtraction sign stays the same. Now I leave the 2 that already existed there. I add through multiplication. I'm multiplying it by the new 2 that comes out, and then we're going to leave our square root of the 3 that got left underneath there. So combining, I've got 9 square roots of 3 minus 4 square roots of 3. Now I do have matching terms here. I've got the square root of 3 and square root of 3, so I just do 9 minus 4 gives me 5, and I leave my square root of 3 in that case, right? So let's go right below it and see initially what can we even look at. Well, I have an index of 4 and an index of 4 and an index of 3. So we can change things that are underneath, but we can never change the index. So right away, I know that my first 2 terms here can be combined, but I will never be able to simplify this guy as long as it has the 3. So we might be able to look at it and see if we can do a little bit more work to change it, but we're not going to be able to adjust it with these 4th roots over here, okay? So let's look at 48. Well, 48 is 12 times 4, okay? And 12 is 3 times 4. And 4s are 2 times 2 and 2 times 2. So if I'm looking for the 4th root, and I still have that little 3 guy, I needed 4. I have 4 2s, so they can escape. So I have a 7 from the original, and now I have a 2 4th root of 3. So it's important that we keep that 4 in that index spot. Okay, now I have minus 2 4th roots of 3. And then let's go ahead and simplify the 72. So 72 is 3 times 24. 24 is 3 times 8. And 8 is 2 times 2 times 2. So I'm looking for something that has 3 of them. So I needed 3. I have 3. I can move those out and be 2 cube roots of 9 is what gets left underneath there. Okay, so again, I can't change this index, so I can't combine any part of the 2 cube roots of 9 there, but we can say that we've got 14 4th roots of 3 minus 2 4th roots of 3, and these can be combined to 14 minus 2 gives us 12 4th roots of 3, and then we're just going to leave minus 2 cube roots of 9 on that, okay? So as we work through these adding and subtracting ones, we need to check the index, check the radicand that's underneath, see if we can simplify a part of it, and then combine our like terms on it, okay? Now, when we multiply, we have a couple of different rules for multiplication, okay? Let's stay on this one. So right underneath, we've got multiplication here, and it says to use the product rule. Well, one of the things that we know about multiplication is that it doesn't matter if the inside is the same. So just like when we were looking over here, and we needed to both have the same index and the same radicand, meaning that same base number underneath. When we are looking at multiplication, that rule doesn't apply. It only has to have the exact same index. And so we're only looking at the value of our radical sign. So in this case, I've got the square root of 27 times the square root of 5. These are the same. They can be combined underneath one radical and be 27 times 5. I'm looking for the square root, and I'm actually going to simplify this because I know this is 3 times 3 times 3. I'm going to pull that guy out, and it's going to be the 3 square roots of 15 is what stays on the inside. Okay, so a couple of different ways. You could multiply this all out first and have 27 times 5 and get 135 for that, and then go to simplify. I like to personally simplify as soon as possible so that I don't have to deal with big numbers, okay? So let's look at 9. We've got 3 as an index, 3 as an index, perfectly fine. Whoops. Sorry, I clicked the wrong thingy for that. So we're going to multiply our coefficients. So 2 times 5 is 10. That stays on the outside. We leave our index of 3, and then we multiply everything that's on the inside. Now, right away, we're looking at a negative 24. Are we allowed to have a negative 24 underneath a cube root? Think about that. Can I have a negative sign if my index is odd? And the answer to that is yes, because I can have 3 of the exact same number. I can have 3 negative 1s that equal negative 1 underneath there, okay? So I've got 9 is 3 times 3. 24 is 3 times 8, right? And 8 is really 2 times 2 times 2. And one of these guys, so for the negative 24, we've got to figure out which one is going to be all exactly the same. So we're going to make these negative 2's all exactly the same. And that would give us 3 times negative 8 would give us the negative 24. So now I have 3 matching 3's, which escape. The 10 has to stay. So he still hangs out. Now a 3 is in line with him. Now I have negative 2's. They're escaping as negative 2. And we got rid of everything that was on the inside. So now I have 10 times 3 is 30. 30 times negative 2 gives me negative 60 is my answer. There. So pretty simple when it comes to multiplying. We're just checking to make sure the index is the same. We're multiplying the numbers together, and we're pulling out everything that we can for it. Now, if we were to change and we're going to combine multiplication and addition and subtraction together, okay, we're going to look at, let's explore this right below here. How would we expand 2 times x minus 4? We would use distribution, right? And you'd say 2 times x, and then we would say it's 2 times negative 4, which would give us negative 8. Okay? Now, when we have 2 minus x times 2 plus x, we would expand that using FOIL, correct? And they would go all the way across, okay? So when we're working with binomials or monomials with a plain variable, it's pretty easy to distribute and expand those out. The rules apply exactly the same when we move into exponents, okay? So, sorry, and radicals. So it doesn't matter if we're working with exponents or if it works with radicals. They're going to work exactly the same. In that, we start out with the square root of 10 here. We're going to use this example times this binomial. So what if we looked at it? What if this was really 10 times 5x minus 2y? Would that be overwhelming? No, we would do 10 times 5 and we'd get 50x, and 10 times negative 2y and get negative 20y in that case, okay? So we're going to use those same rules, and we're going to multiply this guy. So I've got 5 is on the outside, so he stays on the outside, and I have matching indexes. So I can combine these. Square root of 10 times 5. It just all goes underneath the square root sign. My subtraction side stays the same, and my 2 stays on the outside because it's 2 times this 1. This just has a 1 there. Again, the 10 is underneath the radical, so it gets multiplied underneath the radical, and I have times 2. So I am looking here, and before I combine these, I actually want to pull them out because 10 is really 2 times 5. So I have 2 times 5 times 5 under that radical, and here I've got 2 times 5 times 2 under this radical, okay? So I need 2. Do I have 2? I have 2 matching here, so it comes out as a 5. The first 5 stays. It gets multiplied by the new 5, and I've got 25 square roots of 2. Now here I need 2. I've got 2 2's. They come out as a 2. This first 2 stays. He gets multiplied by the new 2, and I end up with 4 square roots of 5. So it comes out with different radicands than what we started with in the first place. The first one started with a square root of 5, and that term ended up with a square root of 2. The second one started with a square root of 2, and he ended up with a square root of 5. But 25 square roots of 2 minus 4 square roots of 5 is a completely acceptable answer for that. So let's look at 17 below here. Okay, so we have 2 binomials, so you can think of this as a minus b times c plus d, and we're just going to FOIL. First, inner, outer, and last on them, okay? So let's do our firsts. I've got 6 square roots of 6 times another square root of 6, so he just goes right underneath. Okay, my outers, I've got 6 times 1, so it still gives me a positive 6, and now underneath my radical I have 6 times 2. My inners here is negative 6 and this 1, so I've got negative 6. Here's my 2 inner radicals, 2 times 6. Then my outer one is still a negative 6, and underneath I have 2 times 2. Okay, well, all of these are square root, which means my index is really 2, so I'm looking for 2. I need 2, I have 2, so this is 6 times 6. I need 2. What do I have here? I've got 6 times 2. Could we simplify this? 6 is really 2 times 3, and then 2. So I do have 2 that I can pull out. I can do 6 times 2, and I have a 3 that stays underneath. Okay, now I have the same thing, 2 times 6 over here, so I've got 2 times 2 times 3. My negative 6 stays. That 2 goes with him. My 3 stays under the radical. Here I have a matching 2, so I have 6 times 2. So 6 times 6 is 36, plus 12 square roots of 3 minus 12 square roots of 3 minus 12. Now, these are constant terms and can be combined into 24. These are radical terms that have the exact same index and exact same base. So these can be combined, and 12 minus 12 is 0, and it just cancels out. So let's go back and look up here that we do have, from the outside, I have 6 plus my outers and my inners. I had a 6 on the outside and then a negative 6, and we're going to end up with the same things underneath. So we could see that those are going to cancel out for it. So with binomials, we're just working through distribution and then using our radical simplification rules to pull them out. Okay. So work through those for your homework, and then we're going to address 6.4 with dividing radicals and rationalizing the denominator in the next